Welcome back. In this video, we're going to be talking about brittle failure theory. So this builds on another idea of static failure theory, in that materials will break within the time frame of a certain constant static load. And this happens to be for if a material is considered a brittle material. So to cover this today, what we're going to do is three things. We need to look at stress concentrations, and then we're going to look at two different theories for brittle failure. Those are maximum normal stress and the modified Mohr. So let's begin with stress concentrations, number one. So we'll talk about stress concentrations quite a bit more, but I want to introduce it now because we'll be using this when we talk about fatigue quite a bit. And stress concentrations exist in a part because of discontinuities. So I like to think of it like water flowing through a creek. So imagine this is your part, and it in fact kind of looks like the path of water flowing through a channel, and you have some discontinuity. So for example, you've got a bolt hole right here. If you imagine the water flowing down through this creek, hopefully you realize that there must be more flow lines around the discontinuity. So these flow lines, in our analogy, are the flow of stress in the part when we put it under some force. And any time we have discontinuities, we have stress concentrations. So anytime there's a load applied to a certain location, or there's a hole or a geometry change, such as a fillet, we're going to have an increased stress concentration there. And that stress concentration tends to lead to crack growth. And so when we look at brittle failure, it's going to be really important because when something fails brittly, what we mean is that a crack grows very quickly. If a part is failing inductally, we're going to find that the static failure doesn't make much of a difference. The stress concentration doesn't make much of a difference. But when we are talking about fatigue loading, which is, again, crack growth, these stress concentration factors are once again going to become important. So stress concentration factors are very simple to use. What we do is we develop a concept of the stress, say, due to the normal loading. In this case, we'd have something like P over A. And what we do is we apply some stress concentration factor. I'll use KT as our stress concentration factor, and multiply that times that normal stress as it would be without, and come up with our actual stress value. So how does that look? What does that look like in practice? Well, if you look in the back of your textbook, or if you have a digital textbook, Appendix A15 looks like this. We have many different types of loading, as you can see on the diagram here, and this is exactly the one that I showed before. There is some force acting on either side of this part. There is a width, and there's a diameter of the hole. So based on the ratio of the diameter of the hole to the width of the part, so how much of the material is actually carrying that stress, we can come up with a stress concentration factor. So if D over W is half, so if the diameter of the hole is about half the width of the part, our KT factor would be about 2.2. So as we go off one direction or another, we can make some approximations based on the way this figure is shaped. So there are a few simple cases which we can match to whatever loading situation we have, and you can scroll through these on your own. So these are all 2D up to 15.4, 15.5, and then we start moving into the 3D case. So we'll look at a lot of shafts in this case, and they're all basically the same. We need to have some nominal stress, so every KT is multiplied times some nominal stress. In this way, the force acting over the area is the nominal stress that this KT is applied to. So you can't apply the KT to any any abstract formulation of stress, it must be according to the graph itself, where this area equals that. And so based on the little diameter to the big diameter and the radius of the fillet, we can come up with what our KT value should be. So in practice, what that looks like is we know the loading F equals 100 pounds, for example. The area equals 25, I don't know, how about 0.25 inches squared. Therefore, our normal stress from that would be force over area. But considering we have this hole, we look at the figure and find out that KT for that hole needs to be about 2.2. Therefore, our actual stress value that we want to use when we start computing principal stresses is going to be 2.2, that's the KT, times that 100 over 0.25. And that will be the actual stress value we want to use. So stress concentrations are important anytime we expect cracks to grow. So in general, we can use sigma max equals KT times sigma naught. Whether that sigma naught is from bending stress or normal stress doesn't matter, or direct axial stress. And our shear stress due to that load will be K, and we use TS for the shear part times the nominal shear, say from torsion, for example. We add it by parts, meaning if we have this situation, which is very common, a round shaft with a fillet that is under both bending and torsion, then we're going to get a KTS from the torsion loading, and we're going to get a KT from the bending loading. And if there was an axial force, we'd have another KT from the axial portion. So the torsion gets multiplied times the normal stress that would be due to that torsion. The bending KT gets multiplied times the bending stress that would be normal to that bending. And the KT times it would be multiplied times the nominal stress that would be due to the direct axial. And then we could put all those things together and come up with what our actual stress values are. Now there's a few exceptions to this. Most notably is cast iron. So cast iron is almost always brittle, and we do not need to use stress concentration factors with cast iron because experimentally, when cast iron has microscopic flakes, and when experimentally they find the ultimate strength, the point, it includes those stress concentration factors. Our other major exception is ductile materials. So ductile materials, if a crack starts to grow, then it leads to relief of local stress. And if we relieve some of that local stress, then it does not yield. When there is a crack and that crack starts to grow, the stress goes higher and higher at the very point of that crack until it gives way, and then it releases that stress. So if it's a ductile material, we don't include the stress concentration factors because they aren't necessary, and they get relieved by the actual microscopic plastic deformations which do happen. So we'll only be using stress concentration factors with brittle materials and materials that fail in brittle ways during fatigue loading. Now let's talk about some of our brittle failure theories. And recall, we consider something a brittle material if the strain at which it fails, if we plot a stress-strain diagram, if the strain at which it fails, let me do epsilon f, is equal to or less than about 0.05, so about 5% strain, is when the material fails. That's what we call brittle materials. So these failure theories are all for brittle materials, as opposed to ductile materials, which will change shape and plastically deform. We are considered mostly with materials that will all of a sudden grow cracks and break. So brittle failures are usually significantly more severe than ductile failures, in the sense that if you imagine standing on ice and it cracks and gives way, it can be very immediate. So brittle failures are often have much higher significance than ductile failures, because if something fails in a ductile way, usually it changes shape slightly and may even gain some strain hardening. And so the thing itself may fail in the sense that it no longer works, but it won't completely give way. So the two approaches that we can look at for brittle failure, the first we'll look at is maximum normal stress. And maximum normal stress is very quick, and it's an approximate. However, it does overestimate the strength of the part, so it is not conservative. It overestimates the strength of the part. Excuse me, it overestimates the strength of the part. So the two steps here, basically, we're first going to find the principal stress, and two, we're going to compare that principal stress to the ultimate strength. So maximum normal stress theory basically says this: anytime your absolute maximum positive normal stress is equal to or greater than the ultimate strength and tension, or another way to say that, the most negative compressive strength stress is less than, in terms of its total value, or equal to the ultimate strength in compression. So ultimate strength in compression is often noted as a positive number, even though it means positive in compression. So don't worry too much about the math here. If it says 30 psi in compression, compare that to 30 psi in compression for the principal stress. If either one of these happens, maximum normal stress for brittle failure theory says that we will have brittle failure. So we just need to check these situations. So what that looks like is, say we have some part, and we put it under some stress, and due to its loading, we can come up with some stress element at a critical location that we care about, and maybe it's, we'll do compression. So this is the total part. This is the stress element. So again, loading, stress, failure theory. Every single one of these steps will be exactly the same. And we'll put some complicated loading situation, such that our stress element here has the stress state of 30, let's call it megapascals, negative 14 in shear, and negative 15 in compression in the y direction. So again, you can use the eigenvalue calculator, or you can use your Mohr circle, and you're going to come up with three numbers. One of those is negative 6.6. Next one will be negative 38.6, and then the last eigenvalue will be 0. So how do these work out? Well, 0 is the most positive, so that's going to be our sigma 1. Negative 38 is the most negative, so that's going to be our sigma 3. And this then must be our sigma 2. So in this situation where our biggest value in terms of where it might fail is in compression, so if sigma 3 is greater than or equal, is less than or equal to the ultimate strength in compression, then we would say it fails. So for example, if this was in PSI, the cast iron material strength in compression is 140 kpsi. So our factor of safety for brittle failure, according to maximum normal stress, would be 140, that's the strength of the material, divided by the most negative that we're under, 38.6. And you can have negative here if you want to keep yourself in compression, but obviously that doesn't make a difference. So this gives a factor of safety for the brittle failure of about 3.6. So in the situation where sigma 1 is positive and sigma 3 is negative, this method overestimates strength and probably should not be used. Instead, you should use the modified Mohr or the Coulomb-Mohr. So let's talk about that now. So modified Mohr. In the same way for Coulomb-Mohr for ductile materials, this is just a way of looking at the combinations of the ultimate strength in tension and the ultimate strength in compression when a part has principal stresses in tension and in compression. So there's a couple cases that make sense here. The first case would be looking at plane stress, is if we've got two values, sigma A, which will be sigma 1 in this case. I'll just go ahead and do that. So sigma 1, which is greater than or equal to sigma 2, which is greater than or equal to 0. So in this case, 0 would be our plane stress. And there may be some other negative ones, but it doesn't matter too much. So if all the principal stresses are greater than 0 or are in tension, then we say this part, modified Mohr says that this theory says that this will fracture if the greatest, most positive one is greater than or equal to the ultimate strength in tension. So that's exactly like the maximum normal stress theory. Therefore, the factor of safety would be the strength of the part over our sigma 1. Case 2 would be when one of the stresses is positive, one of the principal stresses is positive, and one of them is negative. So we've got a sigma 1, which is greater than 0, and we've got sigma 3, in this case, which is less than 0. So again, talking about plane stress, one of the principal stresses has to be 0. This is the case where we need a modified Mohr and where the one from before was inaccurate. So modified Mohr says that this will fracture. That is, it will have brittle failure if this is true. If the ratio of the ultimate strength in compression minus the ultimate strength in tension multiplied times the positive 1, that's sigma 1 in this case, divided by the ultimate strength in compression times the ultimate strength in tension. So we're basically coming up with ratios here. This is obviously our modifying ratio. That's why it's called a modified Mohr. Minus the most negative 1 divided by the ultimate strength in compression. If this ratio is greater than or equal to 1, then we will have fracture. It's equivalent to, we could come up with the 1 over n in that situation. So how far it is away from 1 is our factor of safety. And case 3 is exactly like maximum normal stress. So that is, if all of our values are negative, then we just compare that most negative one and see if it's worse than the strength and compression. And then it'll fracture if it is, meaning our factor of safety would be that strength and compression over our actual stress that we're under. Not all materials are always ductile or always brittle. They can change. So for example, steel can be very brittle if it has a high sulfur content, or if the load temperatures are very low, or under high impacts. Those can all be situations where the stress will be, the energy in it will cause a crack to grow, as opposed to plastic deformation. Well, that'll about do it for our brittle failure theories. Until next time.